Welcome to Chapter 7. If we're looking for evidence of a chemical reaction, we can look at several things that we've looked at in previous chapters. A color change could be evidence, formation of a solid in a clear solution, formation of a gas, the exchange of energy, either the absorption or the emission, and also giving off light. But you need to be careful because not all of these things are always evidence of a chemical reaction. When water boils, I'm producing a gas, but it's the same gas that was the liquid. So all I'm doing is vaporizing. No chemical change has occurred. Same thing can happen if we use food coloring. Put food coloring in water. The color changes, but it's a physical change. We're just spreading out the food coloring. There are no new products made. So let's talk about chemical reactions. We have to break the bonds between the outermost electrons of atoms, and then we reform them in a new way. And so chemical reactions involve changes in matter, which is making new materials. Those new materials have new properties, and there are energy changes. We can use symbols to represent elements. That was early. Then last chapter we wrote formulas to describe compounds, and now we're going to look at chemical equations to describe a chemical reaction. We show the conversion of reactants, which are the substances on the left of the arrow, into products, substances on the right of the arrow. You can use a plus sign to separate molecules. You could also have a plus sign if you had more than one product. The arrow tells us that something reacts, so it is often read as yields or produces. So if I look at this chemical equation, I would read it as carbon and oxygen react to yield, or I could say produce carbon dioxide, and that is what's going on here when we're burning our charcoal. Recall the law of conservation of mass. We can't create it or destroy it during ordinary chemical reactions, nor during physical changes. And because of this, our chemical equation must be balanced. And balanced means it has to have the same number of atoms on the same side on both sides. For example, I have 2 chlorine atoms on the reactant side. That means I must have 2 chlorine atoms on the product side. I have 2 hydrogen. I have to have 2 hydrogens somewhere. And recall that the masses are equal. The mass of the reactants all summed together should equal the mass of the products summed together. Here is a reference of symbols used in chemical equations. We already said that we can use the plus sign to separate reactants or products. Talked about the arrow. This new type of arrow, or the double-headed, is used for reactions that can go from reactants to products or from products to reactants. We can have the state, and here this is a solid. This L, and sometimes it is written as a cursive L because the print L is a little bit difficult to see. We have the G for the gas. If something's dissolved in water, it is aqueous, AQ. If you're putting in energy, you put this means change in. You can just put the delta on top of the arrow to represent it, or sometimes people will write heat. If you have a catalyst that does not take part in the reaction, but is present to speed it up, it is also put on top of the arrow. We can look at a formula equation, which we can write formulas, and then we have a reaction and we have new products. We can also do a word equation. And so this one is the decomposition of ammonium dichromate yields nitrogen gas, chromium 2 oxide solid, and gaseous water. When we're balancing equations, the only way that an equation can be balanced is adding coefficients in front of the compounds. And the coefficient is a coefficient just like in math class. It is a number in front of the formula. You cannot change the subscripts. If we look here, this is methane. This is the gas for our lab tables. And the oxygen's coming from the air. So we have methane and oxygen, and it produces carbon dioxide and liquid water. If we count up our atoms, we have some issues. We have one carbon on each side, but we have 2 oxygen in the reactants, and in the products we have 3. That tells us that our equation is not balanced. We also have 4 hydrogen atoms in the reactants and only 2 in the products. So we're going to put coefficients to make this balanced. So if we put a 2 in front of the oxygen, now we have 2 of these. So we have 1, 2, 3, 4 oxygen molecules. And if we put a 2 in front of the water, we end up with a total of 4 oxygen reactant atoms and 4 oxygen product atoms. We can say there are 2 here, and each water has 1. There's 2 waters, so that gives us 2. If we look at the hydrogen, we still have 4 hydrogen molecules in the reactants, and now we have 4 molecules because we have 2 of the water, which each water has 2 hydrogens. This is the Born-Haber equation, and it is creating ammonia. But this breaks the law of conservation of mass. There are 2 nitrogens on our reactant side and only 1 on our product side. We have 2 hydrogens, and in our product we have 3. We can add any more of a complete molecule, but we can't change it, because if we would change this formula somehow, then you're not making ammonia. So the first thing I would do is I would create another molecule of ammonia. Now I have 2 nitrogens on my product side and 2 on my reactants. So since I have done that, I want to put a 2 in front of the ammonia formula. Well, that solved my nitrogen problem, but now I have 6 hydrogens on this side, or I can look here, I have 2 molecules and there are 3. And so I need to increase the number of hydrogens to 6. So then I have to change the coefficient here to represent 3. It's a good idea when you first start balancing equations if you need to draw the molecules. Pause the video and give this one a try. So if I am splitting water, which we will do later in this chapter, when I split water, I have 2 hydrogens in both the reactants and the products, but I have 2 oxygen in my product side and only 1 in my reactant side. So I'm going to put another water molecule, because that's the only thing I can do, is I can put a coefficient, but I can't change the subscript. So now I have the 2 oxygen. Sometimes I keep track of them this way. So I have 2 here, and now I have 2 here, but I have 4 hydrogen and only 2 hydrogen on my product side. I have to remember to put the 2 in front of there to represent the 2 molecules, and now my equation is balanced. So let's try a little more complex one. Ethanol here and oxygen, so this is another combustion reaction. I'm making carbon dioxide and water. I'm going to start off with my carbon, and I have 2 carbons on my reactant side and only 1 on my product. The only thing I can do here is to create another molecule, so I do that, and I want to make a record of that. I have 2 of the carbon dioxide. So now I have 2 carbons on my reactant side and 2 carbons on my product side. Let's look at hydrogen next. Now you'll see that I have 5 here, but I have an additional one. So I have 6 hydrogen, 1, 2, 3, 4, 5, 6, and I only have 2 on my product side, so I'm going to need to change that to a 3. So now my carbons are balanced and my hydrogens are balanced. Let's take a look at the oxygens. I have 3 oxygens on my reactant side, 7 on my product side. I really don't want to put more of the ethanol molecules if I don't have to. So the first thing I'm going to do is try to balance it with my oxygen. 2, 4, 6, 7. 2, 4, 5, 6, 7. All right, so now I need to adjust my coefficient. The first thing you need to do is when you're balancing equations is you need to write the correct formulas for the reactants and the products. That's the very first step. Sometimes if you find you can't balance it, perhaps you wrote the formulas incorrectly. We're going to work each element at a time. You want to do the other atoms, leave hydrogen and oxygen for last. You want to do hydrogen, and then you want to do oxygen the very last. If you can get everything to balance except for that oxygen, and there's no way to balance it, try doubling the coefficients and try again, because oxygen is diatomic as an element. If you have polyatomic ions, and it's the same, if you have a nitrate on the reactant side and the nitrate on the product side, then you want to balance them as a unit. Once you think you're finished, you want to count your atoms to make sure that it's balanced, and then the coefficients have to be reduced. They have to be the lowest possible whole number ratios. Pause the video and give these a try. So if I look at aluminum, I have 2 products, 1 reactant, so I'm going to put a 2 here and change that to 2. If I look at bromine, I have 2 on my reactant side and 6 on my product. If I put a 3 here, that gives me 6. Let's look at propane and oxygen reacting, combustion to make carbon dioxide and water. If I look at my carbons first, carbon's always a good one to go first. I have 3 on my reactant side, so if I put a 3 here, I have 3 on my product side. Then I'm going to go hydrogen. I have 8 hydrogen on my reactant side, but only 2 on my product side. If I put a 4 here, though, I will have 8. Lastly, I'm going to look at oxygen. It's diatomic, so I have 2 here. I have 6 oxygen from my 3 carbon dioxides, and I have 4 oxygens from the water. That gives me a total of 10. So I'll want to change this. If I put a 5 here, that also gives me 10 oxygen. This time you'll have to write the formula, so you'll be crossing just like we did in Chapter 5 for each reactant and then product. Double check your formulas. Sometimes when you struggle with balancing, it is actually the formula that's incorrect. Let's take a look at sodium. I have 3 sodium atoms on my reactant and 2 in my product. If I put a 3 here and a 2, that gives me 6 and 6. I'm going to balance the phosphate as units. I have 2 on my reactant side, so I need to have 2 on my product side. If I look at iron, I have 2 on my reactant side and 2 on my product. Always saving oxygen for last, I'm going to see that I have 3 on my reactant side. We don't count these because they've been counted as the phosphate. Similarly, over here, they've been counted, so I have 3 on my reactant side and I have 3 on my product side. So I've successfully balanced this. This one, we have the states: calcium metal, metal meaning it's a solid. We have chlorine, remember that's diatomic and it's a gas form. And then in our products, we have calcium chloride and it is aqueous. Pause the video and write the equation. If I try to balance this, I have 1 calcium on each side, 2 chlorine on each side. So it is balanced as written. Notice that we never include ones in our coefficients. Sometimes computer programs, when we practice, will require that so they know that we've done something. But when you're writing them down, you should never write a 1 within it. Pause the video and write the unbalanced equation. Check your formulas and then pause the video again and balance it. When I balance carbon, I have 1 on each side. When I want to balance my hydrogen, I have 4 over here and only 2. But if I put a 2 here, I have 4. Now let's take a look at our oxygen. Since it's diatomic, I have 2. Let's look at our product side. I have 2 and then 2 more, I have 4. So if I add another oxygen, I should have 4, and that should give me my balanced equation. So first we looked at having the atoms and drawing those. Then we did the shorthand where we just did the symbols. And eventually you should get to the point where you can look at most equations and go back and forth and tally them and not have to spend your time drawing or writing the atoms. Be sure to bring your questions to class, and I will see you soon.